Next is Bernoulli's equation. Now see here, when we observe the flow of water in a river, so when the water flows from the wider region of the river, then its velocity decreases. But when the water flows from the narrower region of the river, then its velocity increases. So when the water flows from the wider region of the river, then its velocity decreases, and when the water flows from the narrower region of the river, then its velocity increases. So the scientist name Bernoulli, he observed that when the fluid flows from the narrow region, then its velocity increases. But at the same time, the internal pressure of that fluid in that narrow region decreases. So what Bernoulli observed that when the fluid flows from the narrow region, then its velocity increases, but at the same time the internal pressure of the fluid in that narrow region decreases. So this phenomenon is called Bernoulli's principle. Now see this figure here. This figure shows that an ideal fluid is flowing through this tube here. This ideal fluid is flowing through this tube of varying cross section and height. So see here, the ideal fluid is flowing in this tube here. So this is the flow of that ideal fluid, and this tube is having varying cross section and height. So what is ideal fluid? Ideal fluid is what? The incompressible, then the non-viscous fluid, that is called ideal fluid. So the incompressible fluid and the non-viscous fluid is basically the ideal fluid. So in this figure, there is an ideal fluid is flowing through this tube which having varying cross section and height. This tube is having varying cross section and height. Now we are considering the element of fluid that lies between this cross section P and this cross section R. So we are considering this fluid which lies between the cross section P and R. So we are considering an fluid which lies between cross section P and R. Now we are considering the lower end, which is P here, and the upper end, which is R here. Now see, the lower end P is having cross sectional area A1, and the upper end R is having cross sectional area A2, and these cross sectional areas are the areas of fluid at lower end P and upper end R. Next we will take V1 is the velocity of fluid at lower end P, and we will consider V2 be the velocity of fluid at upper end R. See in this diagram here, this A1 will be the cross sectional area of the fluid at lower end P, and this A2 will be the cross sectional area of the fluid at upper end R here, and this V1 here is the velocity of fluid at lower end P, and this V2 be the velocity at upper end R. Let P1 be the pressure of fluid at lower end P and P2 be the pressure of fluid at upper end R here. So P1 and P2 are the pressure at lower end P and upper end R here. So see here, as P1 is the pressure of the fluid at lower end P here, and A1 is the cross sectional area of the fluid at lower end here, that is P, then there will be a force acting there. So at lower end P, the force we will consider as F1 here, and that should be equal to pressure into area. That should be equal to pressure into area. So we will write F1 is equal to P1 into A1, that will be the force which is at lower end P. And if we consider upper end, now we will write force at upper end, that is F2 is equal to P2 into A2. Now see in this figure here, at the lower end P, the force is P1A1. P1A1 is the force at lower end P, and this force is pushing this fluid in upward direction here. This force is pushing this fluid in upward direction, and the next force is at upper end R here, and this force is P2A2, and this force is opposing this P2A2, which is the force at upper end R. This force is opposing the flow of fluid, due to the force P1A1. So P2A2 is the force which is opposing the flow of fluid, that is due to this force P1A1. So this force P2A2 is what it is, the inertia force. It is the inertia force. So this force P2A2, that is the inertia force, this will oppose the flow of fluid which is due to force P1A1, and this force is acting at the upper end R here. As the force P1A1 is acting on a fluid at lower end P, this force P1A1 will push this fluid from the lower end P in this upward direction. See here. So this force P1A1 will push the fluid which is at lower end P in the upward direction. So there will be a displacement of fluid. So in time dt, the fluid will displace from this lower end P to Q here, and this displacement is given by d1 here. So we will write at lower end P here, the displacement of fluid in time dt, that is d1 here. Now see at the upper end R here, there is a displacement of fluid at upper end R, and that is from R to S, and this displacement is given by d2 here. So d2 is the displacement of fluid at upper end R here, and this displacement of fluid is due to this flow of fluid which is in the upward direction from this cross section P to R. So this displacement d2 is in the opposite direction, to this inertia force P2A2, and this displacement of fluid is due to this flow of fluid which is from the cross section P to R here, the cross section P2R, and this flow of fluid is due to this force P1A1. This force P1A1 which is acting on the fluid at the lower end P. So we can write here the displacement d1 should be equal to velocity v1 into dt. dt is the time interval and v1 is the velocity at lower end p here, velocity of fluid at lower end p. Next we can write here this d2 is equal to v2 into dt, because v2 is the velocity. v2 is the velocity of fluid at the upper end R, and the fluid is moving from R to S in same time interval dt here. So because of that, d2 is equal to v2 into dt. Next point in this, as the fluid flowing in this tube is the ideal fluid, that is, it is incompressible fluid. So because of that, the density of the fluid is constant throughout. So we will consider here rho is the density of fluid here. Rho is the density of fluid. For this incompressible fluid which is flowing in this tube here, we can take the equation of continuity here. We can take the equation of continuity, and from the equation of continuity we can write here the mass of the fluid in this section PQ here. See this section PQ, that should be equal to the mass of the fluid in section RS here. Mass of the fluid in section RS. See in this diagram, this is section RS which is at the upper end here, and this section PQ which is at the lower end. So the mass of the fluid in section PQ is equal to the mass of the fluid in section RS here. So we can write here the mass of the fluid in section PQ, that will be density of fluid rho into A1 into V1 dt here is equal to, we can write here mass of the fluid in section RS as rho, that is density, into area A2 into velocity V2 into dt. So this rho that is density on both sides will be cancelled here. So we can write here A1 V1 into dt, that should be equal to displacement d1 here is equal to we can write here A2 into V2 into d2, V2 into dt, that should be equal to displacement d2. And this product of area A1 into d1, we can write this as it is the volume of fluid. It is the volume of fluid in section PQ here, and this product of A2 and d2, it should be the volume of fluid in section RS. So the volume of fluid in section PQ and the volume of fluid in section RS both are equal here, that is A1 d1 is equal to A2 d2. So we will write it as A1 d1 is equal to A2 d2 is equal to dV. So this dV is the volume of fluid which is passing through this section PQ and section RS. So A1 d1 is equal to A2 d2 is equal to dV, and we will take this as a equation number 1 here. We will take this as a equation number 1. As the force acting on a fluid at lower end P and upper end R here due to the pressure P1 and P2, the displacement is produced. So there is a displacement of a fluid here. So as the displacement of a fluid, then there will be a work done. And the net work done and the net work done by the fluid when it is flow from this lower end P to upper end R, that should be equal to work done by a fluid at lower end P plus the work done by a fluid at the upper end R here. So we will write here the work done should be equal to the work done at lower end P, and that should be equal to here force F1 into displacement D1. What is work done? Force into displacement. So at lower end P, the force is acting here F1 and the displacement is D1 here, plus the work done at upper end R here. So the work done at upper end R here, that should be equal to force F2 into displacement D2. But this force F2 is having opposite direction with the displacement of fluid, that is D2, at the upper end R. See here, the force F2, that is P2A2, is having opposite direction with this displacement of fluid, that is D2. So D2, displacement of fluid, is in upward direction, and the direction of force F2, that is P2A2, is in downward direction. So we have to take here force as negative, that is minus of F2 into D2. So the work done by the fluid at the upper end R, that should be equal to minus of F2 into D2. We will write here work done W is equal to, what is F1? F1 is equal to P1 into A1 into D1. This plus into minus, it will be minus here. And what is F2 here? F2 is equal to P2 into A2 into D2. Now we can write here W is equal to P1 into, what is A1 D1. According to equation number 1 here, we can write A1 D1 is equal to volume dV minus of P2 into, what is A2 into D2, that should be also equal to volume dV according to equation number 1 here. So we can write the work done W is equal to P1 minus P2 into dV. If we take dV common here, then W is equal to, that is work done is equal to P1 minus P2 into dV. And this work done W is the work done by the fluid when it flows from the lower end P to the upper end R. And as this fluid is in motion, so this work done W, according to work energy principle, this work done W is equal to the change in the total mechanical energy, So which are the types of mechanical energy? As this fluid is in motion here, so there will be a change in the kinetic energy. And as this fluid is moving in an upward direction, so the height of the fluid is changing with respect to time. So there will be a potential energy also. So we can write this work done W is equal to the change in kinetic energy plus the change in the potential energy. So this work done W is what? It is equal to the change in kinetic energy plus change in potential energy. So we will take this equation of W, that is equal to change in kinetic energy plus change in potential energy, as equation number 3 here, and this equation of work done is equal to P1 minus P2 into dV. We will take it as the equation number 2 here. Now next step we have to do, that is, we have to find out this change in kinetic energy and change in potential energy. So first of all we will find out the change in the kinetic energy, and this change in kinetic energy is equal to the final kinetic energy minus initial kinetic energy. So what is final kinetic energy? The kinetic energy in the section RS, that is the final kinetic energy, minus the initial kinetic energy is the kinetic energy in the section PQ. So change in kinetic energy is what? It is the final kinetic energy, that is the kinetic energy in the section RS, minus the initial kinetic energy, that is the kinetic energy in section PQ. Now we will write the change in kinetic energy is equal to, what is kinetic energy in section RS? So what is the formula for kinetic energy? That is equal to 1 by 2 mass into velocity square. So we will write here 1 by 2. So what is mass here? The mass of fluid in section RS, and that should be equal to the density rho into volume of fluid. What is mass? Mass is density into volume. So density rho into the volume of fluid in section RS, and that volume of fluid in section RS is equal to A2 into D2. That is the volume of fluid in section RS. So this is mass, that is density into volume here, into velocity square. So velocity of fluid in section RS will be V2, and it should be V2 square here, minus the initial kinetic energy, that is the kinetic energy in section PQ. So we will write it as 1 by 2 mass will be here density rho into volume of fluid in section PQ, that should be equal to A1 D1, and the velocity of the fluid in section PQ, that should be equal to V1, and we have to take the square of that velocity here. So this will be the change in kinetic energy. This will be the change in kinetic energy. So we can write this change in kinetic energy as 1 by 2 density. What is A2 into D2? According to equation 1, it is equal to volume. So we will write dV here into V2 square minus of 1 by 2 density rho. What is A1 into D1? According to equation 1, it is also equal to volume dV into V1 square. Now if we take the 1 by 2 into density rho into volume dV common here, then we can write the change in kinetic energy is equal to 1 by 2 into density rho into dV. In bracket it should be equal to V2 square minus V1 square. So we will take this as a equation number 4 here, and this is the change in kinetic energy. This is the change in kinetic energy. Next we have to find out the change in potential energy, and that change in potential energy is equal to the final potential energy in section RS here minus the initial potential energy which is in section PQ here. So we can write this change in potential energy as, this is equal to, what is final potential energy in section RS. So what is formula for potential energy? It will be mass into height into gravity, or mass into gravity into height, that is mg into h. Now see here, what is mass of a fluid in section RS, and that mass of a fluid in section RS, that should be equal to density into volume, that is A2 into D2. So this will be the mass of a fluid in section RS, that is density rho into A2 into D2. Then gravity will be g here, gravity will be g into height. Now what is the height of this section RS? What is the height of this section RS from this baseline here? See here, this height is H2. This height is H2. So we will write here H2 minus the potential energy in section PQ. The potential energy in section PQ, that is the initial potential energy. So that is also equal to mass into gravity into height. So we will take mass first. So mass of a fluid in section PQ, that should be equal to density into volume. So volume will be A1 into D1 into gravity into height of section PQ from this baseline here, and that is equal to H1. So we will write H1 here. Now next step in this, the change in potential energy is equal to density rho. What is A2 into D2? According to equation 1, we will write it as volume here into gravity into H2, that is height, minus rho into that is density into what is A1 into D1. According to equation 1, that should be also equal to the volume dV into gravity into height H1. If we take the density into volume into gravity common here, then we can write the change in potential energy is equal to density into volume into gravity in bracket H2 minus H1. We are taking the density into volume into gravity common here. So change in potential energy is equal to the density into volume into gravity in bracket H2 minus H1, and we will take this as a equation number 5 here. We will take this as a equation number 5. Now if we substitute the equation 2, 4 and 5 in equation 3. So if we substitute equation 2, 4 and 5 in equation 3, then we can write here P1 minus P2 into dV is equal to what is change in kinetic energy, that should be equal to 1 by 2 density rho into volume. In bracket we will write V2 square minus V1 square plus we will write change in potential energy as density rho into volume into gravity, density rho into volume into gravity in bracket H2 minus H1. Then we can write here P1 minus P2 into dV is equal to, if we take dV common here, then we can write in bracket it should be 1 by 2 into density rho in bracket V2 square minus V1 square plus density rho into gravity in bracket H2 minus H1, bracket complete. So we will complete the final bracket here. Now this volume dV and this volume dV will get cancelled. So we will write here P1 minus P2 is equal to 1 by 2 into density rho into V2 square minus V1 square, that is in bracket, plus the density rho into G in bracket H2 minus H1. So the equation, that is P1 minus P2 is equal to 1 by 2 into rho, that is density in bracket V2 square minus V1 square plus rho, that is density into gravity in bracket H2 minus H1. This equation is called as Bernoulli's equation. This equation is called as Bernoulli's equation. So this Bernoulli's equation, we can write it as P1 minus P2 is equal to 1 by 2 rho into V2 square minus 1 by 2 rho into V1 square plus rho into G into H1, H2 not H1, minus rho into G into H1. So if we take here P1, if we shift this minus 1 by 2 rho into V1 square on left side, so then it will be plus 1 by 2 rho into V1 square, and if we shift this minus rho into G into H1 on left side, then it will be plus of rho into G into H1 on left side here is equal to, if we shift this minus P2 which is on left side on right side, then it will be plus of P2 plus the remaining terms are 1 by 2 rho into V2 square, 1 by 2 rho into V2 square plus rho into G into H2. So this equation, Bernoulli's equation, we can write it as P1 minus P2 here is equal to, if we multiply this bracket V2 square minus V1 square by this 1 by 2 into rho, then we can write 1 by 2 rho into V2 square minus 1 by 2 rho into V1 square plus, if we multiply this bracket, that is H2 minus H1 by rho into G, then we can write it will be plus rho into G into H2 minus rho into G into H1. Now we will shift this one minus of 1 by 2 rho into V1 square and this minus of rho into G into H1 on left side here, then we will write P1 plus 1 by 2 rho into V1 square plus rho into G into H1 is equal to, we are shifting this minus P2 on right side here, then it will be plus of P2 plus the remaining terms are 1 by 2 rho into V2 square plus rho into G into H2. Now we will take this Bernoulli's equation as a equation number 6 here, and this equation, that is P1 plus 1 by 2 rho into V1 square plus rho into G into H1 is equal to P2 plus 1 by 2 rho into V2 square plus rho into G into H2 as equation number 7 here. So from this equation number 7 we can write the pressure P plus 1 by 2 into density rho into velocity square plus density rho into gravity into height is equal to constant, So from the Bernoulli's equation we can derive the equation, that is pressure plus 1 by 2 into density into velocity square plus the density into gravity into height is equal to constant. So this equation, that is pressure plus 1 by 2 density into velocity square plus plus density into gravity into height is always equal to constant. Now finally we have to define this Bernoulli's equation. So what is Bernoulli's equation? That is P1 minus P2 is equal to 1 by 2 into rho in bracket V2 square minus V1 square plus rho into G in bracket H2 minus H1. So we can define this Bernoulli's equation as the work done per unit volume of a fluid is equal to the sum of change in kinetic energy per unit volume and change in potential energy per unit volume that occurs during the flow of the fluid. Here again, this Bernoulli's equation, that is P1 minus P2 is equal to 1 by 2 rho, that is density in bracket V2 square minus V1 square plus rho into G in bracket H2 minus H1. We can define this equation as the work done per unit volume. The work done per unit volume of a fluid is equal to the sum of change in kinetic energy per unit volume and change in potential energy per unit volume that occurs during the flow of fluid. So this is the statement of the Bernoulli's equation. This is the statement of the Bernoulli's equation, and this is all about the Bernoulli's equation.